So hello everyone. So in last video I started with a common source amplifier voltage gain calculation if the load is resistive type. So but this in last video I only covered the ideal model. I only covered the ideal model, means no CLM was considered. So in last video CLM was not considered, means CLM was means lambda was 0 in last video. And second thing, body effect was not also considered. Body effect was not also considered. But in this video, I'll consider both the effects together and how these effects will modify a small signal model. So actually this CLM, when lambda is non-zero, it will introduce the output impedance inside the small signal characteristic, which is nothing but equal to 1 upon lambda ID. So this is your value of uh, R naught, that is output impedance. The body effect will introduce some kind of transconductance, that is GMB, the body transconductance. So, okay, if I introduce these two effects extra additionally in this, then how this small signal will be modified? So, in the last video, it was like simply this small signal was like this was your gate and this source was grounded, a small signal. So this was your VGS, and here Vin was applied. And in the small signal, only this current source was there, which was GM, VGS, and after that, nothing was there. We simply taken the output. We simply taken the output across the load RD. But in this case, if we have also considered these two effects, CLM and body effect, then I introduce one more resistance. Okay, so in this particular thing, so this is your basic model. Here we have VGS, one current source here, that is your GM VGS. And second thing is here, this R naught, it is due to 1 upon lambda ID. So lambda is non-zero, means this R naught will come into the picture. And second thing, this current source, GMB BBS. So this is your drain and this is your source. This is your source. This is your gate where Vin is applied. And this is your drain. And after that, we are taking the output across this RD. V out. Okay. So now, the last time the model was only this limited value. So last time, this model was this much only. In last figure, this was the model. But now, this complete is the model. Now, this complete is the model. And after that, load is taken here to take the output. So how to take these values of BBS and GMB into the picture? So first of all, I'll tell you the meaning of this BBS. So BBS is what? The difference between body and source voltage. So when we simply consider this NMOS, its source is grounded or source is connected to the least potential. This is your gate, this is your drain, this is your source. And it is recommended that source should always be connected to the lowest potential. So source is connected to zero potential in this case. So it is also recommended that body should also be at the lower potential. If your body is at zero potential, then we'll see that this body is also at zero potential. Then we'll see that BBS, that is a body potential minus source potential, is zero. But if somehow your source is at higher potential or body is at some different potential, if this body potential and the source potential are not equal, then we'll get this term VBS as a non-equal, not equal to zero. In that case, this term of GM VBS will come into the picture. So this is the basic concept. So now, how we will draw this thing? If you want to see this thing over the small signal, then I can say if this is a gate, this is the drain, and this is your source. Suppose this is your source, and this is your source. This is your gate, and let's suppose your source is at some potential, or can say zero potential, and you have body here. So body is suppose at some negative potential, can say, and or can say minus suppose 0.5, and this is your zero potential. This is your minus 0.5 potential. Now we can say this GM VGS. This VGS is nothing but a potential between this gate and source, VGS. But this BBS is what? BBS is nothing but a potential between this. BBS is nothing but a potential between this body and source. So if body had some lower potential than the source, then this term will be in the negative, and body has the higher potential than the source, it will be the positive. Simple logic. So this is a general consideration we can consider. There's a body at the lower potential than the source. If body at the higher potential, then we can also draw this body terminal here. Then we can draw the body somehow, somewhat here. So now this is the body, and in that case, we can also draw the body there in between. So this can also be the body. In this case, this body at the higher potential, so this BBS is positive. So overall, this thing is going to be introduced inside the small signal model. Then how we'll apply this basic KVL? So now this ID current is entering here. This ID is not here. Don't be confused with this thing. This ID is not here. So basically, this is incorrect. The ID is because this complete is the model of your MOSFET. This complete, so ID is entering here. So this MOS is completely modeled like this. What the red bracket. So ID is entering here. Means if you write the equation, then you write for ID, we will write, what we will write? So suppose this is the point also we should know here. So this point potential is same as the V out because this potential wire is shorted. So this is also V out. So we can write one KCL, sorry. ID is equal to GM plus and your V out, that is your higher potential or the potential over this side of your R naught, and this side potential is zero. This side potential is zero. So I can say V out minus zero divided by R naught. And third thing is your, and yeah, GMB. So third term is your GMB BBS. So this is the one equation that we'll draw for ID. And the second equation is your ID minus ID multiplied with RD is your V out that we have drawn in last video also, that we written last video also. So this is the second equation. And after that, one is a KVL equation that you write between these terminals. So third equation is a KVL equation. I'm writing it here. Third equation is V in equal to VGS. So from these three equations, we can draw the expression for V out by V. That is your voltage gain with body effect and channel length modulation. So I think this is the basic concept behind the consideration of channel length modulation and body effect inside the this model of your voltage gain calculation. So I think this is enough for this video. Next video, I will consider this same body effect and this simple calculation for PMOS also. So this is enough for this video. Thank you.